Good afternoon, everybody. Many thanks for taking time to join us on today's technical WebEx, which covers all the business sectors that we work in. The presentation lasts about 40 minutes with a Q&A session at the end. If you think of a question as we're going on, please use the messaging facility, which is on the system, and we will get to you at the end of the presentation. Okay. My name is Steve Musa. I'm the Business Improvement Manager. This is a technical WebEx and it will be run mainly by my colleague Jayesh Nandwala, who is our Technical Director. But first of all, I'd like to just run through this afternoon's objectives. We're going to cover the business sectors that we work in the UK, the business divisions that make up CC UK, Composite Construction UK in the UK, the design principles of working with carbon fibre. We'll touch on what we can strengthen, and we'll give you some really good project examples and some video. Within the project examples, as I say, we cover all the business sectors. And finally, at the end, we will have a Q&A session. So these are the business sectors that we work in, and there are 5 business sectors in the UK. Buildings, which is by the largest of our business sectors, which covers off probably around about 70% of our current turnover. So where you have a change of purpose, change of use, offices are going to become apartments or hotels, additional floors to increase a building size, or additional M&E services or requirements. And we'll show you some really good examples later on. But just at the point I was mentioned, this is not just about old buildings. We're seeing a big increase of new build structures that have to have structural retrofit, and this is an ideal solution to use carbon fibre. Transport and infrastructure. In the UK, this generally covers bridges. Over the years, we've completed several bridge strengthening projects throughout the UK. Waterfront structures, if you have any clients who own or manage property or assets that are structurally damaged or potentially could be damaged by water, we have several bespoke solutions that can be used to significantly increase and protect that asset. Power and energy, covering oil, gas, and the nuclear industry. We mentioned this to emphasize how difficult to get into some of these marketplaces, and the power, energy, and especially nuclear industry are those industries. And finally, pipelines and water storage. Similar to waterfront structures, these type of projects we work on all over the UK for various water industry companies. Very small part of our business, around about 5%. The business divisions and CC UK, obviously today is about the strengthening side, the use of carbon fibre, the Gfrp. But we just like to touch on very quickly something which is driven by by our clients, is the concrete repairs division within CC UK. This business has grown over the last 2 to 3 years, and we've had clients who have come to us and specifically asked, well, if you're doing the repairs to the concrete and whatever you do, can you actually take this work on? And that's something which is developed. So if you would like us to give you a presentation on the concrete side of our business, this is something that we'd be pleased to set up. I'll touch on very quickly the history, or we like to say the DNA of our company. It was formed in 1988 back in the USA, and Jayesh will touch on that, how it's actually developed. In 1999, we were established in Europe, in Athens, but in 2010, that's when we were born, basically, and we've now been working for well over 10 years. But the business itself has been operating for over 30 odd years. And again, Jayesh will run through the timeline in more detail during the presentation. So at this point now, I just want to hand over to our technical director, so Jayesh. Jay, are you there?
Yeah, thanks, Steve. Good afternoon, everyone. I'm Jayesh, Technical Director from CC UK Fibre. I'll deliver this presentation because this is a technical presentation and we want to explain you how the fundamentals of carbon fiber strengthening and how it is used and where you can use it in different scenarios. Um, so before we go into too much detail, as Steve said already that this is an all sector presentation. So the case studies you will see will be from all the sectors which Steve has mentioned before. But the elements of which you strengthen pretty much remain the same. So it will be beam, column, slab. So they all will be the same, but they'll be in different environment. So before we go into the detail of that, I just want to touch on some basics of CFRP, that what CFRP is. So basically carbon fiber or carbon fiber reinforced polymers, CFRP in short, is a very high strength and lightweight material, and it is a composite material. So the basic composition will be like a fabric mixed with epoxy resin, and then you apply it onto the structure from the outside of a structure. That's why it is called externally bonded reinforcement, or EBR for short. And it can be used on concrete, steel, wrought iron, cast iron, even on timber structures. So pretty much any construction material you can strengthen using carbon fiber. We have done a jetty strengthening in Portsmouth Naval Base, which was a timber jetty, so you could strengthen timber elements as well. The another misconception people have generally is that this is a very new material or a new technology. That's not true. This was first used in 1944 in aerospace engineering. And then in 1988, founder of our previous company, Fife and Fiber, Mr. Ed Fife, was the first person to use it in construction. And that was basically on the request of Caltrans, which was California Transport Association. They wanted to save their bridges from earthquake. And that's how the FRP came into the construction industry. The bridge piers were strengthened and then retrofitted for seismic and everything. And the other advantage of using carbon fiber is that this is very low profile material. The typical thickness of one layer of carbon is 1 millimeter. So imagine if you're able to strengthen a beam, column, or a slab with one layer of carbon, it means you're increasing its dimension by just 1 millimeter, which is negligible as compared to other traditional method of strengthening of using new steel sections or concrete jacketing. So that's why architects also prefer using carbon fiber because it doesn't change the profile of the structure that much. And ultimately, it is a very economical solution if you see the whole cost in terms of material, labor, disruption to your structure, and most importantly, time in doing that strengthening. So the main advantage you get in carbon fiber strengthening is basically the time, because you can do carbon fiber strengthening in days or weeks as compared to the months or year for traditional method. I will go in some more technical basics now, how basically it works, how you design it, and all those things. So first thing is the approvals and acceptance. So the systems I'm going to show you in this presentation are FiberRep systems. They are the only system available in the market which are ICC approved, which is International Code of Council, which is the governing body for all the design codes. We do have some fire protection systems as well, which are UL rated. So you can use the fire protection system if you need fire protection after strengthening of an element, and they are up to 4 hours fire rated. In terms of the design guidelines, if you're designing it in the UK, then the document to follow is this Concrete Society document TR55. That's the design guideline to design FRP in the UK. But then you also have FIPL 1840, which is followed in the rest of the Europe, or ACI 440, which is an American Concrete Institute document. So majorly, these are the three design guidelines which are used worldwide to design FRP. And if you know what I'm saying, they are design guidelines. They are not design codes yet. So currently a team from UK who wrote the TR55 is working to put an annexure in Eurocode 2. So hopefully by the end of this year, we will have a Eurocode 2 to design FRP, which obviously will bring more confidence in carbon fiber or use of carbon fiber in construction. This is the typical stress strain behavior of FRP in comparison with mild steel. We all know this black curve or behavior of steel. That's the yield point where we designed all the steel. And then top green line you're seeing here is the carbon fiber. The bottom green line is for the glass fiber. So from this curve, you could see that carbon is stronger than steel and glass has better deformability or ductility, if you like. So based on this curve and the requirement, it is decided which material to use and at what strain level it should be designed, because FRP is a strain limit design. The other reason to do it as a strain limit is purely because FRP has a linear elastic behavior until its rupture strain. So nobody wants FRP to break or have that kind of brittle failure. That's why it is designed based on the strains. You're limited to the very low kind of stresses, and ultimately the brittle failure will never happen onto the FRP. And that's the reason it is a strain limit design. Similarly, this curve here explains the very first thing I said, that this is a composite material. So you have at least two materials mixed together to make FRP. So you'll have a dry fiber, which could be carbon, glass, aramid, or Kevlar, or even basalt these days. And then you will mix it with epoxy matrix. And once they cure, they will become like an FRP. So the ultimate design you're doing should be based on these final cured laminate property and not just dry fiber property, which is a common mistake done by the designers in the past. They've just used the dry fiber property to design their strengthening system and ultimately ended up applying less FRP than actually required, and it didn't work. So that's why I always make sure that it is designed based on final cured laminate property and not just dry fiber. This is the design information we request from you. So if you come to us with any inquiry or any queries relating to use of carbon fiber for any particular requirement, this is the information we will ask you. That what sort of an element you're looking to strengthen, whether it's a beam, column, slab, or wall. Then what is the section information of that particular element, thickness, span, what is the existing reinforcement in that, the grade of concrete, grade of steel, what kind of loads it currently has, and what you're looking to put onto it. And for our final design, we would also need the load at the time of strengthening. That is to make sure that you're applying carbon fiber at a time where steel is already stressed and strained. So we need to know that how much it is already strained, so that FRP strain will be governed by that, and that's one of the serviceability check. And ultimately, any restriction in applications. For example, if you ask us to strengthen on top of the slab, is there any riser opening around the area, or there is any wall, which we need to keep in mind so that we can design our carbon fiber anchors accordingly and all. So all this kind of information we need. Once we get this information, we'll do a preliminary analysis of feasibility study to first of all check whether carbon fiber strengthening is an option for that particular scenario or not. And if it can be done or if it is feasible to use carbon fiber, we will let you know the time required to do that strengthening and also the budget cost for design, supply, and installation of the material on site. So everything is done by us, and that's why the whole responsibility remains with us. We can provide the PI insurance for up to £10 million on our designs. So that's one of the advantage that why you should work with us, because we take all the responsibilities and liabilities in terms of the design and installation. So if in future anything goes wrong, you know who to contact, and there are not like 2-3 parties involved to do just one small job. Right, we'll see now what can be strengthened. So this is basically the elements or different types of inquiries we get. So the most common is slabs and beam strengthening. So the slabs can require strengthening for additional loads and for sagging moments or hogging moments. These days we do a punching shear strengthening as well using carbon fiber. So in this image you could see all this strengthening is done basically for punching shear. This slab strengthening example is for sagging moment strengthening. And then this is the beam strengthening example, which is done for flexor and shear. So for flexor, FRP is at the underside, for the shear on the sides. So very simple schematic of the beam strengthening is this, that if you're looking to strengthen it for additional sagging moments, then you'll apply FRP on the tensile face, which will be at the underside. For hogging moments, it will be on the top. And the top strengthening will always be anchored into the ends or the supports so that it has a continuity there and not just stopped at the support. And for shear strengthening, assume like putting a link or a stirrup from the outside of a beam, but in form of carbon fiber. That's why it's called U-wrap application. And we can use our anchors drilled into the beam or into the slab to provide a similar effect as in closed loop. So that's how we do the shear strengthening of the beams using carbon fiber. Here's an example, a project example for the beam strengthening. This is from Selfridges in London, Oxford Street. They were doing some refurbishment on this building, adding additional stories, so the beams were getting additional point loads and were generating additional moments, so they needed strengthening for sagging and hogging moments. So that's what it was done there. So we applied FRP at the underside of these beams to increase their moment of resistance in sagging, and also on top to increase their moment of resistance in hogging. And also, as I said, that at the end or near the column, FRP was anchored into the column so that there is a continuity, because this is the place where you'll have the peak moment, and you don't just want to curtail the FRP at the location of the peak moment. Otherwise, there's no point in doing that strength. And these anchors you are seeing they are basically required to justify one of the checks or serviceability checks according to TR 55, which was basically for shear crack induced FRP separation. So we provided anchors in form of like providing a U-wrap. And the shear strengthening was done in application of U-wraps. It was applied like a U-shaped fabric from the outside, and they were also anchored into the slab to provide the additional anchorage or ultimately the additional strain there. I'll show you some of the materials which we have used in that project. So generally the most common material used in terms of concrete strengthening or for example concrete slab or beams is this carbon fiber wrap system. So it is like a dry fiber system. It comes on a roll. It will be 600 millimeter wide, 90-meter length. So you have the flexibility to cut it in any size and shape. Then you saturate it on site using the epoxy, and once it is wet, you will apply it onto the structure. So it's called wet layup application. An application should always be wet layup because the previous practice of doing dry layup led to many sort of debonding or delamination failure, because there would be dryness in the fabric which you cannot tell when you're just doing the dry layup method. That's why we always do wet layup application. The other material you may have come across is carbon fiber plates, which are pre-cured carbon fiber plates. They come in a fixed width and length, so you don't have that flexibility to cut it or mold it in any size and shape because they're already cured. So these plates are generally used when you're strengthening metal structures like steel, wrought iron, cast iron, or even in concrete structure when you have very narrow width available there. So for example, clay pot and beam construction, that's where you can use these pre-cured plates. And the last but not the least is the material which we use basically for protection of waterfront or underwater structures. This is glass fiber reinforced polymers or GFRP. This system was developed to do the seismic retrofit in US and other European countries, but in UK we know that seismic is not a major design concern for us. So that's why here in the UK this material is generally used for protection of elements from weathering actions. These are the fiber anchors we have. I've shown you in the previous slide the anchors which how we have used them. But generally these anchors are used either for shear strengthening or to transfer the force from one side to another side or to anchor like a particular amount of force. So in this case we were strengthening the slab for hogging moment. So we use these bigger anchors, drilled hole through the column, pass these anchors through these columns and splay on both sides like a dovetail and put one more layer on top of it. So these anchors are acting as a tie which is transferring force from this side to that side, and there is a continuity of reinforcement. So whenever there is a peak moment on this side or that side, you still have the continuity of the reinforcement, and there will be no like abrupt stop of carbon fiber strengthening. Similarly, this was a shear core wall strengthening, and in that as well, from every floor from top to bottom, we use these anchors to transfer strengthening from the floor above to floor below using these anchors. And then this is very simple schematic view of these anchors, of the blind anchors which we use for shear strengthening. It's basically we drill a hole through the concrete, we saturate the anchor, put half of that anchor into the drilled hole and split the remaining half on the face and put one more layer on top of it. So now this anchor is going into the concrete and it will cure simultaneously with the FRP. So the whole system will become like a laminate along with the anchor. So it will provide you huge resistance and pull out force. So it provide additional bond capacity or the anchorage. These are the range of epoxies we have. The Type 4 is our most common epoxy we use for saturation application in normal climatic condition, normal structures. But we have some special epoxies as well, like this one, SW1S. This is a special underwater epoxy. This is used mainly for waterfront structures or the structures where we have water contact issue or something, because this epoxy can cure in presence of water. So this was developed specifically to provide that sort of capability to the epoxy to cure in presence of water. Because whenever you're working in a waterfront environment, you have to work with the tides. So whatever strengthening you have done will get submerged in 4 to 6 hours. So we need something which can cure in presence of water. That's where we use this epoxy. And this is the fire protection systems we have. So as I said that they all are UL rated. We have two types of fire protection systems. So one is an intumescent paint coating system, which is FCF, It's 2 hours fire rated, and you could see on this column, this was strengthened using carbon fiber, and this the fire protection system applied on top of it. It's just like a paint coating. Uh, and then we also have the cementitious fire protection system, which is more like a barrier kind of system that is up to 4 hours fire rated. So it's three different materials sprayed onto top of the carbon fiber to get up to 4 hours fire rating. And typical thickness of this kind of system will be around 20 to 25 millimeter to get 4 hours fire rating. This is another project for slab strengthening. This is another London project. It's Blythe London, which is in Hayes and Harlington. It's a new build structure, and it's, as Steve said, that these days we get many inquiries on the new build as well because of a construction error or a design error or anything. So in this case, basically, this was a new concrete frame building, as you could see here, which was built in 2014. After the construction of this building, the contractor who was doing the construction gone into administration. So their work was checked before passing it on to the another contractor, and they found when they checked the work is that they missed the reinforcement in the flat slab. And by missed, I mean they missed or they forget to put around 4,500 square millimeter reinforcement in many locations. So like in this one area, they forget to put around 2,000 square millimeter of steel on slab. So this structure was pretty much condemned, and they asked them to demolish and rebuild. But obviously, you can imagine the cost of demolition and rebuild, and also the 40 million pounds which client has spent so far in, making or in constructing this frame will be of no use. So we worked with the new consulting engineer there, and then designed each and every location for lack of reinforcement and for resistance of punching shear. And it was done using carbon fiber. And there were around 380 locations in this whole tower block, which was done using carbon fiber. We saved a lot of time and money by not demolishing and rebuilding the structure for the client. And again, it was the most economical solution for them. Here is a brief video of application just to explain how it is done. So first thing you do is grinding of the substrate. So take all the smooth latins off, and then you do priming. After cleaning the substrate, you do priming of the area using epoxy. So this is a pure epoxy they are using. Now white color stuff you're seeing is the thickened type of S epoxy. That is thickened using silica fumes, and that is used so that the bond between the different layers of FRP and FRP in concrete can be increased. So once you've done put the first coat of typho WS epoxy, you put first layer of carbon fiber, which is, as I said, it's saturated. So you saturate it before applying it on top of it. So the roll you are seeing, they all wet fabric. And then once you unroll it, you just squeeze it out the additional epoxies, put another coat of epoxy on top of it, and then you keep on following until you put the number of layers required as per the design on this. So once that is done, you can leave this area to cure, or if it is in like an environment of waterfront or in like chemical environment or something, you put protective coating on top of it if required. Otherwise, you can leave it exposed like this, and once it is cured, you can plaster it, paint it, render it. You can do anything on top of it. Like in this area, they were going to put screed back onto it, and that's why we cut the chase down so that the level of the screed and everything would remain same throughout the floor. Similarly, this is another example. This is a beam strengthening now, and it's from a sluice gate structure, which is more like a bridge type of structure. So in this case, you can see there are three gates supported by two of these precast concrete beams on each gate. There were major stress cracking in these beams. They were not able to lift these gates up and channelize the water. Uh, and that's why they wanted to do strengthening of these beams, so that because this was part of a major flood relief work and they needed these sluice gates to operate as soon as possible. So they designed their traditional solution of putting another steel section underneath these beams here. But you can imagine, to put those steel beams in place, you need access all the way around this structure. You also need, a lot of health and safety constraints are there in terms of lifting and fixing of those beams in place. So we designed a solution using carbon fiber, and we found that we need three layers of carbon fiber at the underside of this beam to provide the moment of resistance they are looking for, and then encapsulate the beam with glass fiber to protect it from weathering action, so there is no future, spalling or falling off of the concrete or anything. That was done using FRP, and we did that work from the MUP. So we didn't need scaffolding or anything, so saved a lot of time in that scaffold kind of thing. and then did one gate in 1 week. So in 3 weeks, this whole structure was strengthened. Probably 3 weeks would have been the time they needed to put the scaffolding up there. So again, you see the time you've saved there, and how quickly they were able to use this structure by doing it with carbon fiber strengthening system. Similarly, this is another inquiry we get, which is the service penetrations or riser openings through existing RC slabs or shear cores. So in this case, they wanted to create this door opening through a shear core, and that was strengthened using carbon fiber. Similarly, here they were doing service penetrations through precast, through the flat slab, and in that case, they needed strengthening. We all know the traditional solution to do this kind of strengthening is design some trimmer beams, transfer it to surrounding beams, and that's how you deal with this situation. But the same thing you could do with carbon fiber as well as done in this case. So the concept behind here is that whatever rebar you're going to cut with these openings, you design FRP for the force generated by those rebars. So that's why you apply FRP first on all four sides, and then they cut these openings, so that as soon as you cut the rebar, the stresses will transfer to the FRP. You will have no localized concentration. So you could see the time you save there in terms of temporary works, propping, and all those kind of things. So that's how you do this strengthening using carbon fiber in this scenario. Here's an example for that particular case. So this is from a tower block or a council tower block from Wolverhampton Council. As we all know that after the unfortunate tragedy of the Grenfell Tower, it is a requirement now for all the councils to try and put a sprinkler main in all the tower blocks and change the facade as well. So to put this sprinkler main, they need to core through existing RC slabs, and we all know that these tower blocks are occupied, so you cannot go with trimmer steel option there and then do these kind of service penetration there. So FRP is the best and easy option there to strengthen these slabs for the loss of rebar or the additional moments generated in the surrounding area, and that was done there. So we applied FRP on all three sides with anchor into the end core wall, and then they cut these cores so that there was a strengthening system available for any additional stresses. So again, it took us 3 weeks to strengthen this three tower blocks there. So we did one in 1 week. So again, saved a lot of time there, and also they didn't have to ask the tenants to move out for a longer period of time. Then comes column strengthening. So the column strengthening is probably one of the easiest strengthening to do with carbon fiber, because it works on confinement theory, and that's why circular is the best shape, because the stress is even on all the sides. So all you need is the closed loop of carbon fiber and minimum overlap as per TR55, and that's how you strengthen it. So but once you confine the concrete, it becomes confined concrete and its strength increases. And ultimately, when the concrete strength increases, the axial load bearing capacity of the column increases. So that's in a nutshell the design concept of strengthening using carbon fiber. The same theory you can use on square and rectangular columns, but you have to round off these corners to a minimum radius of 20 millimeter, and also the aspect ratio has to be less than 2. Because if it is more than 2, then you have to go with the more complex analysis of combined axial and bending. Here is an example for column strengthening. It's Laser House, another London project. So these columns are basically steel columns encased in concrete, and that concrete encasement had nominal reinforcement of longitudinal rebars and the stirrups there. But again, as in Eurocode, it is stated that if the concrete encasement has the minimum reinforcement prescribed in Eurocode, then you can account for the capacity of that encasement as well in load bearing capacity. So engineer tried to do that, but again the strength of the encasement was not sufficient to give them the required capacity. So we did the strengthening of this encasement. So we confined this column, increase the strength of the concrete confinement by confining it, and then ultimately they got the capacity they needed. So it was just a very minimum 2 layers of carbon fiber applied there on each column, and they got the required capacity there. Here is a brief video of column strengthening. So again, same concept there as well. You first prepare the column by grinding and then cleaning. Then you round off the edges and corners to a minimum radius of 20 millimeter. The first application process will be priming, then application of thickened type OS epoxy, and that will followed on by the already saturated fibers. So it's because it's a strengthening for axial load, the FRP will be applied in hoop direction. So once you applied the first coat of thickened epoxy, you apply first layer of carbon fiber, again press it against the concrete column. So squeeze out all the epoxy or excess epoxy, then put another layer, and that's how you keep on applying until you get the ultimate number of layers as per the design. Because it's a vertical and overhead application, the maximum layers you can apply in one day is 3. Because after 3, the saturated weight of fiber is too high and it might slide down or it might fall off. That's why you have to wait for at least it to initially set before you apply further layers if there is an application more than 3 layers. So in vertical and overhead application, you're limited to 3 layers in per day. So once that is done, then you can leave the column as exposed like this, so it will be black in color, or you can put plaster paint or render over it, or you can put fire protection coating on top of it if it is required. Here's another example for column strengthening. This is basically a multifaceted kind of strengthening. So it's from Clayton Hotel in Birmingham. Again, there was a major refurbishment going on one side of the hotel. They were putting additional stories on top of it, and some of the beams were getting additional loads due to new columns being installed on top of them. So beams needed strengthening for flexure, and also the ground floor column needed strengthening because they were getting increased axial load because of the weight of the additional stories. So the columns were circular, and that's why they were strengthened using the same confinement theory. It was the straightforward strengthening. The beams were strengthened for additional point loads and for shear, and also we did some sort of shear strengthening there using carbon fiber as well.
Jay, we class as a hybrid system. I know we were working with WSP on this project, but why did we have to go down this route?
Yeah, so it was basically they needed to do some sort of punching shear strengthening as well around these columns, and that was their solution to go with these post drill fix kind of Hilti shear studs. But the slab was pre-stressed, and when they went to drill these holes to put those studs in, they were hitting so many tendons. So pretty much this solution was not practical for them. So they asked us to look at this strengthening as well with the FRP. And we did the strengthening using carbon fiber, but the only condition was that the punching shear failure should not be happening at the face between column and the slab. And in some location it was, so that's why I put some steel collars there to move that punching shear failure away from the column so that FRP can pick up that load. And that's why it was like a hybrid solution. This is another example for column strengthening. It's another high-rise structure. So it's a new build structure again. It's a very tall building in London, Vauxhall. So in this case, basically, it's a very common issue which happens on many new build structure, that during the construction period of the structure, things changes, or architect will change something or client will change something. So the same thing happened here on this as well. The initial plan was to put the plant on the roof on this corner, and that's why all the columns here were designed to take that load due to plant. But nearing the completion, the client decided that they want to put the plant on the other corner of the building. And the columns which were there, they were not designed to take that load. So this was the ultimate column, which was at the ground floor or the lower ground floor, and that was getting additional axial load for which it is not designed for. So that's why they had to strengthen this column. So because it's an existing construction site, they asked their contractor on site to do a concrete jacketing there. And they said they can do that, but it will take them 2 weeks to do that. And then after that, they have to wait for 28 days at least before they can put the load on it. And the plant was already in the transportation, and they were waiting for it to arrive so that they can put it back on next week. That's why they asked us to do this strengthening. We did this work with FRP over a weekend. So we started on Friday and finished on Monday. And on Thursday next week, they put the plant on the roof. So that was the quickest way for them to strengthen it.
Jay, just as an addition, the actual columns that had to be strengthening, what was actually going on there? What forces were, why did they have to do that?
Yeah, so all the columns there were casted using C40-45 concrete. But when they reassessed them with the plant load, these particular columns, they found that they need to be at least C47 to take that axial load. That became our design brief. We had to take the concrete strength from 40 to 47 to make it work, and that's what we did by applying FRP in hoop direction. Another example for column strengthening, this is now on a bridge on a motorway. It's A69, concrete repair and protection. So basically, we all know on the motorway bridges, they are susceptible to the spray and splash and everything of the salt and grit as well. So the concrete get damaged, reinforcement get exposed and everything. And these are central reservation columns. So they were not able to afford any loss on them. So we did the concrete repair, but at the same time, to protecting them from any future damage, if you just go with standard concrete repair, that will only provide a service life of 5 to 10 years. So to increase the service life, we used the glass fiber systems there. So we first did the concrete repair and then wrapped them using glass fiber in their splash zone only, so that they will never damage again, because the glass will protect the water or moisture to go inside the column and there will be no future damage to the column. That's how in the protection a glass fiber was used there. Similarly, this is another bridge example. So this is P-Zone bridge in Scarborough, North Yorkshire. It's an arch bridge with 4 of these concrete arches. Then they have the secondary beams supporting the bridge deck. So they checked this, assessed this bridge a few years ago, and they found that this is failing in accidental wheel load scenario, and that is purely because if the vehicle go and hit the parapet, that will generate a negative moment on the on the on the bridge deck, which is on the transverse direction, not in the primary direction, and there was not enough reinforcement in that. So we strengthened this bridge deck between these secondary beams throughout the arch span. So it was like a big project for us. So it was around 900 square meter of carbon fiber was used to increase the moment of resistance of the bridge deck. Here's an example for pier strengthening. This is from Gosport. So it's a shell pier. Basically, they were going to put a new radar tower on top of this jetty, and then these columns under that were getting additional loads, and also there was major spalling in them. So first, the concrete repair was done. So you could see after repairing these column heads and columns, at the same time, they wanted protection of them because they were in a tidal zone, so they needed protection so that they should not get damaged again. And also in some cases where the rebar was exposed and corroded, we had to strengthen them using carbon fiber as well for the loss of section in the rebar. So first it was the concrete repair done, then we applied the carbon fiber strengthening system, and ultimately put the waterproof epoxy coating on top of it, so that to increase its service life, and also that epoxy can cure in presence of water. So that's how this particular waterfront project was done. Here's another example. This is Royal Portbury Dock, Bristol. Similar issue in that as well. So basically, just to explain a bit of background on these piers there, which you could see, uh, when they casted them in 1960s, for some reason they were overcasted. So they had a huge section which obviously they did not need it there. It was probably a failure of formwork or something. Uh, but in that 50 years of service life, they lost that overcasted concrete due to waves and tidal action and everything. And now whatever section is left there is pretty much the section they need from the design for the loads on the structure. So all they wanted from us to protect them from any future damage or erosion. So that's what we did. We just cleaned these sections, take out any sharp edges or everything. They did not want it to bring it back in any shape or anything. So that's why it was just after cleaning, we just wrapped them using glass fiber reinforced polymers. So glass fiber is just acting as a membrane outside this concrete column to protect it from any future erosion. That's how it was done. Similarly, this is an example from industrial infrastructure. It's a nuclear power station in Haitian. So they had this particular area where they had around 8 concrete beams which were supporting big gantries, um, and then because of that nature, and they were also close to the waterfront. They were waterfront, all of them. So they were in a very adverse kind of climatic condition and environment. So the concrete was getting uh, eroded, and there was major spalling and corrosion in the reinforcement. So they needed to strengthen it because the equipment on top of these beams was quite important. So it was basically a nuclear facility, but the strengthening we've done was mainly for the waterfront structure. So we strengthened that using carbon fiber strengthening system purely because of the outage they could afford was very small, and they could not go with traditional method of strengthening of putting additional steel section on top of it. Uh, and that's why again FRP was used purely because of the time constraints they had. The strengthening done there was both flexor and shear. The flexural strengthening was done by applying FRP at the underside, and shear strengthening by applying a URAP. And these are the finished section images for them. Similarly, another example of an industrial facility. So this is pipe this time. It's from Eon Power Station in Corners Keys. So these are basically cooling water pipes which are connected to cooling tower. They are steel pipe encased in unreinforced concrete, and the purpose of these pipes is to take the seawater back into the sea. And because of the nature of the seawater, the internal steel pipe was getting corroded, and they were losing the thickness of that internal steel pipe. So they had a fear that one day they will lose the whole pipe completely, and the outer concrete encasement, which is not reinforced, will be exposed to very high pressure, and they might have a burst out failure and lose the cooling tower completely. So this was more or less like a fail-safe kind of design. So they asked us to design this carbon fiber strengthening system to take the 3 bar pressure. So just in case if they lose the internal pipe, there is still some sort of reinforcement outside which will stop the burst out failure. And that's what we have done. We applied the carbon fiber again in the hoop direction to increase its capacity and to provide a 3 bar pressure capacity, and also reinforce its concrete. And ultimately it was coated with again a waterfall coating. We'll see some quality control tests and checks which you do after application on FRP. So generally FRP is tested for 2 types of failures. So one is debonding and delamination, which happens especially in the bond critical application if the fabric is dry or if the application is not done properly. So for that test, what you do is a normal pull-off test. So on every strengthening you do, you put a sacrificial patch next to it so it cures in the same environment and everything. And after the 100% curing of FRP, you go and do a pull-off test. So in this particular pull-off test, this is slightly different from concrete pull-off test we do. In concrete, we get a pull-out strength, which tells us that how strong the concrete is. In this case, basically, we're just testing the bond between FRP and concrete. So all we want to see is that when you pull it off, it should not come out from substrate only, or it should not come out from another layer of FRP if there are multiple layers. So in this case, you could see when we pulled it off from the side of this beam, it took out some concrete with it, which shows that in future, if anything fails, that will be the concrete due to crushing and not the bond between FRP and concrete. That's the pass criteria for this test. And then the second test is basically to check the material properties, that whatever material you have designed your system based on is actually used on that project. So the requirement as per TR55 is to cast these 12-inch by 12-inch plates or sample plates. And currently the requirement states that you need to cast 2 plates per roll of fibers or 2 plates per day if it is less than a roll job. You send it to independent laboratory, they'll cast a coupon out of them like this and do a tensile test. And those tensile properties should match with the data sheet. And that's the pass criteria for this test. And finally, these are some of the questions we get, can we drill through carbon fiber? Can we fix through carbon fiber and all? And our answer to this is that no, you should not cut through or drill through carbon fiber. It doesn't matter whatever you say sometimes, how many contractors goes and do this. So you could see here, but in this case, they've cored through carbon fiber. So all we want to say is that if you're going to fix through carbon fiber, please let us know in advance so that we can design around it and we can design for it. So what we will do is we'll put some additional carbon fiber in this area so that when you core through this, there will still be FRP or sufficient FRP available there. So the repair of them is also easy. We will go back and apply additional layers on the sides, but it's always better to do it in design stages rather than going back and do it retrospectively. I think that's about it from my end. I've covered everything, so I'll pass it back on to Steve.
Thanks, Jay. There's quite a lot for you guys to take in with this being an all sectors presentation. We covered off all the business sectors and all the examples. There's quite a lot for you to take on board and that. But I just want to finally, we'll come at some summary points for you. We're the leader. We're the leader in structural FRP design, and hopefully that's come across. We support you. We will protect you, and that's something which we need. We'd like to get over. We offer you obviously design protection, as Jay's gone through, but we also offer you commercial protection. We'll work closely with you to make sure you get the right solution and right commercial profile is used. Um, we're, we're seeing more and more clients who are have got problems. They've gone to material suppliers who'll give them design software which is not fit for purpose. This is quite important, but we'll work with you. We know this is not your area of expertise. A complete and durable and economic solution, a one-stop shop, design, procure, install and guarantee. Less obtrusive. You've seen some great examples. We don't need heavy plant and equipment, and often we work in densely populated work areas which are open to the public. And this reduces not just our carbon footprint, but the carbon footprint of the project. Systems and procedures and testing these underpin our business. Millions has been spent over the years on research and development, and not just in the US, but also in the UK and Europe. And we've worked with several of the UK's universities developing carbon fibre property systems. And when, where, and why? Well, as we've shown, we'll take away your data, we'll advise, we'll work with you, and we'll get the best option for you and your project. And why not? Well, it's free, as Jay went through before. We work with you. We'll give you a solution, and then it's up to you guys. So finally, last slide. We just want to touch on something which is becoming more increasingly on the radar of everybody. On a regular basis, we're asked about the carbon footprint or the impact using carbon fibre or CFRP has, and here are four key points that we believe. Using carbon fibre gives a viable alternative to change of purpose projects, and they can tick all the boxes with architects, structural designers and contractors. Manufacturing and production of carbon fibre uses significantly less water and heat if you compare it to steel and concrete. With it being lighter and more flexible, it's easy to move, so we don't need any big wagons or craneage required on our or your projects. And there's a big cost saving on there because we're seeing more and more we're able to reduce the program of a project. And finally, sort of ongoing research to recycle and reuse carbon fibre. I mean, this is something that, again, we're actively involved with several people. So that was it. As I said, it lasted just over 40 minutes, so we weren't that far off. But we always like to say it's about ideas. We don't know what types of projects that you guys are working on currently, or maybe have in the past. But hopefully you've seen something today which sparks an idea. Thanks again, everybody. We really appreciate you connecting today. Hopefully we'll be speaking with you in the near future. Thank you very much.